What if the most famous ship in history is not preserved at the bottom of the sea, but being eaten alive by it? That question does not belong to science fiction. It belongs to the present tense. Right now, 12,500 feet beneath the North Atlantic, a process more patient than anything humans have engineered, is quietly dismantling the RMS Titanic piece by piece, bolt by bolt, deck by collapsing deck. The ship did not simply sink and stop. It entered an environment so hostile that it began a second death the moment it hit the seafloor on the 15th of April 1912, and that second death has never stopped. It is happening right now, in absolute darkness, in silence, with no witnesses except the organisms that have colonized her hull and the robotic cameras scientists send down on rare expeditions to check her pulse. The 2024 expedition by RMS Titanic Incorporated, the company's first return in 14 years, came back with over 2 million photographs and a finding that stopped researchers cold. The iconic bow railing had lost a 5-foot section on the port side. It did not crumble gradually. Multi-beam sonar confirmed it fell as a single piece, now resting on the seafloor directly below, like a tooth dropped from an old jaw. "We are saddened by this loss and the inevitable decay of the ship," the company said. That word inevitable is the one that matters. Not possible, not likely, inevitable. To understand why, you have to understand where Titanic actually is. The wreck lies in what oceanographers call the bathypelagic zone, the midnight zone, beginning around 3,300 feet and extending to roughly 13,000. Titanic sits approximately 3,800 meters down, in a place that is not simply deep in the casual sense. If you stacked 9 Empire State Buildings on top of each other, the roof of the 9th would barely clear Titanic's deck. The nearest sunlight is more than 2 miles above the ship. Below her, the ocean floor slopes downward into Titanic Canyon, carved by cold western boundary currents that now sweep continuously across the wreck, scouring sediment from her hull. The darkness, there is not the darkness of a room with the lights off. It is a complete, permanent, physical absence of photons, a darkness that has persisted every second of every day for over 113 years. The water temperature holds near 1 degree Celsius, the cold of an environment insulated from solar energy for geological timescales, where metabolic processes slow and chemical reactions change their rates. The entire physical logic of the place operates under different rules, but cold and darkness are almost peripheral concerns compared to the pressure. At 12,500 feet, the hydrostatic pressure is approximately 375 to 400 atmospheres, between 375 and 400 times greater than the air pressure a person feels on a street corner in Chicago. Translated into terms Americans recognize, roughly 5,500 to 6,000 pounds per square inch bear down on every surface at the wreck site. For reference, a great white shark clamps its jaws at an estimated 4,000 pounds per square inches. The ocean around Titanic pushes harder than that against every square inch of her hull, every plank, every porthole frame, every rivet from all directions simultaneously, with absolute geometric uniformity, never pausing, never relenting. When the Ocean Gate Titan submersible imploded near the Titanic site in June 2023, killing all 5 aboard, it took milliseconds. The pressure at that depth does not compress structures, it annihilates them. Carbon fiber and titanium failed instantaneously. The transition from alive to gone happened faster than the nervous system can process pain. And yet, this is the counterintuitive heart of the story. Pressure alone is not what is killing the ship. The human body cannot survive at those depths for reasons that have nothing to do with fear and everything to do with physics. Above roughly 300 atmospheres, the physiological mechanisms that allow human cells to function break down at the molecular level. Cell membranes, which rely on precise lipid arrangements to regulate what enters and exits each cell, become destabilized. Enzyme function is disrupted. Even in a perfectly pressurized suit with unlimited oxygen, a body returned from that depth would face lethal decompression injuries from dissolved gases expanding in the bloodstream. The ocean at Titanic's depth is not simply unwelcoming to human life. It is a zone where the fundamental chemistry that makes human life possible does not operate correctly. This is why every expedition requires a vehicle that maintains 1 atmosphere of internal pressure while its hull bears the full crushing load of the deep. Every spherical pressure hull, every titanium frame, every conical viewport exists purely to create a 1 atmosphere bubble in a 400 atmosphere world. Yet life exists at those depths not despite the pressure, but alongside it. When Robert Ballard first found the wreck in 1985, scientists expected something close to a sterile site. What they found instead was a wreck already transformed into a functioning deep-sea habitat, covered in structures that looked like rust-colored icicles hanging from every horizontal surface. Ballard coined a name for them: rusticles. They are not rust in the simple chemical sense. They are living architecture complex formations housing entire consortia of bacteria and fungi operating cooperatively. At their peak, the bow section alone supported an estimated 650 tons of rusticle mass. The dominant organism is Halomonas titanicae, formally classified as a new species in 2010 by researcher Henrietta Mann at Dalhousie University. It feeds directly on the iron in Titanic's hull, oxidizing it and secreting an acidic slime that carries ferric oxides downward, building those characteristic hanging formations as oxidized iron precipitates out. The rusticles are not decorating the ship, they are consuming it. Studies found they release between 0.02 and 0.03% of their biomass per day as iron dust and biocolloidal slime, active biological processing of the ship's fabric, running continuously, 24 hours a day, for over a century. The broader ecology of the wreck extends well beyond bacteria. Sea cucumbers patrol the sediment in the slow style of abyssal scavengers, ingesting organic particles that drift down from above marine snow. The continuous gentle rain of dead plankton and decayed matter that forms the primary food supply for deep-sea ecosystems. Brittle stars, whose 5-armed silhouettes look like living snowflakes against dark metal, filter feed across the debris field. Rat-tail fish hover near the wreck with the unhurried confidence of animals that have no natural predators and no reason to rush. Cold water corals of the genera Chrysogorgia and Lepidopsis grow from debris at up to 10 millimeters per year. Squat lobsters of the genus Munidopsis, pale, translucent crustaceans, caught in an evolutionary negotiation between shrimp and crab, appear more commonly at the wreck than at the natural rocky reef nearby, suggesting they have specifically adapted their foraging to exploit the ship as habitat. Deep-sea fish in the midnight zone carry anatomical adaptations that make surface fish look overbuilt. Thinner bones, absent swim bladders replaced by lipid-filled organs, cell membranes rich in unsaturated fatty acids that remain fluid in cold. Some produce trimethylamine oxide, TMAO, a compound that stabilizes proteins against compressive forces that would otherwise denature the molecular machinery keeping cells alive. The rat-tail, fish, and grenadier that circle Titanic carry these adaptations as standard equipment, evolved over millions of years to make the midnight zone their permanent address. What Titanic has become, accidentally, over 113 years, is an artificial reef. A 2025 peer-reviewed study comparing megafauna at the wreck with a newly discovered volcanic seamount nearby, the Nargiolet Fanning Ridge, detected on sonar by the late explorer Paul-Henri Nargiolet nearly 3 decades ago, found that the natural ridge hosted significantly higher biodiversity than the wreck. Artificial reefs attract and concentrate life, but the community they support differs compositionally from what evolves on natural rocky substrates. The wreck has high densities of squat lobsters. The ridge hosts sea urchin species rarely found at the wreck. These are not interchangeable communities. They reflect different ecological logic responding to different structural environments. What makes Titanic ecologically valuable, despite this, is its role as a stepping stone, a hard substrate in an otherwise soft sediment abyssal plain, allowing larvae to settle and species to disperse across distances they could not otherwise bridge. Larvae from corals on Titanic's hull potentially colonize the next available hard substrate, creating chains of biological linkage across seafloor terrain that would otherwise be uninhabitable for sessile organisms. Titanic is not just a reef. It is a node in an ecological network spanning the western North Atlantic deep sea. The geological context of the site adds a dimension expedition reports rarely capture. Titanic Canyon was carved not by rivers but by turbidity currents, massive underwater sediment avalanches that periodically strip material from the continental shelf. The western boundary current sweeps across the wreck continuously, shifting direction and producing eddies that scour corroded metal away rather than letting sediment accumulate. Salt corrosion accelerates the process. Chloride ions in seawater drive electrochemical corrosion of iron, while galvanic corrosion, where contact between metals of differing electrochemical potential drives one to corrode preferentially, adds a third vector of attack. The ship is being chemically decomposed at the molecular level, mechanically scoured by deep currents, and biologically processed by iron-eating bacteria simultaneously. The cumulative effect is acceleration. Each structural collapse exposes fresh metal to bacterial colonization and current action. As Mann explained, when one level deteriorates, it drops onto the next, which bears the additional weight and collapses in turn, exposing another level to the environment. This is not linear decay. It is exponential. In 1995, Mann projected Titanic had approximately 30 years before complete disintegration. By 2019, she revised that to 15 to 20 years, noting the trajectory was accelerating. Her final assessment was unambiguous. Eventually, there will be nothing left but a rust stain. This is not metaphor. The iron in Titanic's hull will be fully oxidized, the compounds washed away by current and dissolved by seawater chemistry. What remains will be a mineral shadow on the seafloor, an iron-rich sediment layer, slightly elevated above the surrounding plain, marking the outline of where one of the largest ships ever built once lay. Scientists studying iron cycling in deep-sea sediments will detect this signature for centuries after the visible wreck vanishes. The ship will not disappear. It will dissolve back into the ocean's own chemistry, becoming a stratigraphic anomaly that geologists will eventually read as a thin, anomalously iron-rich layer dated to the early 21st century. The wreck has functioned since 1985 as an unplanned laboratory across multiple disciplines simultaneously. Halomonas titanicae has opened research into biocorrosion with direct implications for undersea pipelines, oil platform foundations, and transoceanic cables. Cold-water coral growth rates, documented on the debris field, provide baseline data for deep-sea coral recruitment that was nearly absent before systematic Titanic expeditions began. The discovery of the Nargilette Fanning Ridge emerged directly from sonar surveys conducted during Titanic dives and has since been identified as a vulnerable marine ecosystem containing indicator species, large sponges, Gorgonian corals of the kind international fisheries bodies use to identify areas requiring protection from deep-sea trawling. The 2024 expedition deployed LiDAR scanners, sonar arrays, and hypermagnetometer sensors to produce the first comprehensive three-dimensional map of the entire 15-square-mile debris field. The ship is not just a relic. It is a long-running, uninterrupted, natural experiment in deep-sea ecology that scientists could not have designed or funded independently. All of that science recedes for a moment when you consider the simple fact that the bow is still recognizable. After 113 years of 375 atmospheres, after 113 winters of near-freezing water, After more than a century of Halomonas titanicae consuming her hull from the outside, in the bow of Titanic still rises from the seafloor like a ship. The capstan is still there, the anchor chains still hang. The forward mast, bent by impact, still points ahead at an angle that communicates velocity even in stillness. A bronze statuette of the Roman goddess Diana, 2 feet tall, the centerpiece of the first-class lounge, was found by the 2024 expedition in the debris field, still largely intact, rediscovered in the final hours of the last day of the mission. And the captain's bathtub, that intimate, human-scale detail that became a symbol of uncanny preservation, an ordinary fixture from an ordinary private space, kept intact in extraordinary darkness, was photographed on expedition after expedition for decades. And then one day it simply was not there anymore. Consumed, returned. The ocean does not preserve things forever. It absorbs them, slowly or quickly, depending on what they are made of and how they died, until the distinction between the object and the ocean floor becomes semantic and then disappears entirely. The ocean keeps everything, eventually not as museum pieces, but as chemistry, as dissolved iron ions in a seawater column, as carbon atoms incorporated into bacterial biomass, as silica secreted into the skeletons of deep-sea sponges that have been growing on the debris field for decades. What the ocean is doing to Titanic right now is what it does to everything that enters it on a long enough timescale. It is not destruction, it is transformation. One of the most technologically sophisticated objects ever constructed by the civilization of 82 feet of steel, 29 boilers, a grand staircase, a Turkish bath, 2,224 human beings, is being returned, atom by atom, to the ocean that has always owned everything underneath its surface. The pressure is not destroying Titanic. The pressure is being patient. Here at Sunken Realms Deep, we believe the most extraordinary stories on Earth are the ones happening right now, in places we cannot reach in the midnight zone, where pressure turns physics into poetry, and the boundary between history and geology is just a question of time. If the ocean's patient work on Titanic made you think differently about depth, about time, or about what it means for something to endure, consider sharing this with someone who needs that perspective today. The deep sea does not ask for attention, but it rewards the ones who pay it.